Hello everybody, and welcome to my talk, Testing Multiverse Theories, the Problem of Researcher Degrees of Freedom. My name is Simon Friederich. I'm an Associate Professor of Philosophy of Science at the University of Groningen in the Netherlands with a background in theoretical physics. And I'm recording this talk for the conference The Multiverse from Home. My talk has three parts. I will first give you a very brief motivation for considering multiverse theories in the first place. I think this is useful even though for participants in this conference there is, of course, some intrinsic motivation to study multiverse theories to begin with. I will then briefly review the argument from fine-tuning for life for multiverse theories. I written the Stanford Encyclopedia article on this topic, so it might be interesting for you to briefly hear my perspective on it. And finally, the meat of the talk, the main point is the prospects for testing concrete multiverse theories. My thesis will be that the prospects for testing them, for finding good evidence for or against such theories are pretty bad, are pretty bleak, but maybe for reasons that are not so far really appreciated well. So I think I have a slightly more nuanced take on this than, for instance, multiverse critics such as Peter Voigt. What I will tell you can mostly be found in my book, Multiverse Theories, a Philosophical Perspective, that came out in 2021 with Cambridge University Press. It contains, of course, also much more than what I will present in these few minutes. So why are multiverse theories interesting and important? Why should we consider the prospects for testing them? Well, we do basic physics, like high energy physics, looking for beyond the standard model theories, or cosmology, then it's important to be transparent about our assumptions about what kind of thing we are studying in the first place. Right? What kind of thing are we studying when we investigate the entire causally accessible universe? There are two very different possibilities here, which I call option 1 and option 2. Option 1 would be that we study something that is representative of all that there is, in the sense that the laws and values of fundamental parameters and maybe the cosmic boundary conditions, in as much as they are relevant, so that they are uniform. The values of the constants, such as Newton's constants, or so, according to option 1, would be the same everywhere to what we have in the cosmos, not only where we have causal access to, but also beyond. Right? So there are regions definitely to which we don't have causal access. Maybe there are entirely there are places in a wider sense to which our universe here is not even spatio-temporally related. So and then the conditions might be different there. Option 2 would be that the causally accessible universe is highly specific and perhaps unusual in certain ways. So the laws of nature, so the fact that, for instance, the standard model of elementary particles gives a pretty good description of phenomenology, for particle physics phenomenology, could be something that holds here, but not otherwise, not elsewhere, right? Not beyond the region to what we have causal access, or maybe in spatial-temporally distinct regions. Which option we believe to be true matters a lot for what we see as worthy of an explanation. So, for instance, if we would like to get a motivation for the value of Newton's constant, or say some quark mass, whatever, and then we assume that this is a universal value, then the kind of explanations that we will consider are very different from a scenario where we think that this might be just the value might be here, what it is, but might be very different elsewhere. The kind of maneuvers that we consider will be very different. And I mean by multiverse theory, in the broad sense of this talk, just some version of what I called option 2 on the previous slide. So just theories according to which the laws and constants and maybe aspects of the boundary condition are environmental. So not in the sense of the environmental movement, of course, but just either varying over space-time or varying over multiple spatial-temporally separate universes. Right. So why should we consider multiverse theories in the sense of option 2? One might doubt this because there is no direct evidence for varying laws and constants, or there is some say that there is a slight evidence, for instance, for the value of the fine structure constant or so, but there is no really compelling evidence as far as I'm aware. See, for instance, the reviews by Uison. I think the newest was not quite up to date, but from 2011. is quite useful in this regard. There are good reasons to take the multiverse theories seriously in the first place. The first reason is just that it's a theoretical possibility. Right? We can consider this possibility, and then if we consider the most general the general space of theories that might be viable, then those theories are definitely in that space. The second motivation, that gets a bit more concrete, is that, as is widely known, the combination of string theory and models of eternal inflation seems to suggest something like a multiverse theory. Susskind calls this the landscape multiverse. So if string theory has this huge space of vacua that might be realized in different island universes that emerge in an ever expanding, overarching background of eternal inflation, and at the level of laws, of the level of the standard model or so, these different vacua might correspond to different laws and constants, values of the constants. So to the extent that string theory and eternal inflation have an independent motivation, they seem to suggest a multiverse, a version of the multiverse hypothesis. I'm not going to comment on how good that motivation is, but it's often given. And finally, I'll say a bit more about this in what follows. The idea of multiverse is suggested as an answer to observations according to which many constants or aspects of the cosmic boundary conditions seem to be fine-tuned for life, not in the sense of there necessarily being a fine-tuner or a god or so, but just in the sense that had they been slightly different, then life as we know it wouldn't have been possible, and also typically there would just have been much less structure in the universe, so maybe also less possibility for any kind of life to emerge. So these claims are somewhat controversial, but to give some concrete examples of constants for which they have been made, since the 60s and 70s or so, as the relation between the strength of gravity and electromagnetism seems to be potentially such a constant. The strength, the relation between the strength of the strong force and electromagnetism, which is very crucial for nuclei and for the periodic table of elements, and therefore, for life, is in particular very important. Like which elements which nuclei are stable, which elements exist, and so on. Then Q, a number that measures primordial inhomogeneities that are very important for the extent to which galaxies form, to what extent the ability of the of the universe to transform baryonic matter into galaxies. That depends on this quantity, which seems to have been around 10 to the minus 5, and had it been something like 10 to the minus 3 or 10 to the minus 7, then there wouldn't have been anything like the galaxies that we find here apparently. These are arguments, for instance, from checkmark and Wilczek. So this would be another thing that has not so much to do with a standard model, but more with cosmic, like what you might say, boundary conditions. And finally, maybe the most important and most famous example is the cosmological constant, for which theoretical arguments suggest a very large value compared with what's actually found, which is also not zero, right? But also important for galaxy formation. This is also considered something that might have an explanation, not in terms of more fundamental physics that we haven't yet discovered, but in terms of a multiverse. So how would this explanation go? The idea is that, well, if you have just a single universe, then it's pretty remarkable that the constants just happen to have these specific values that allow life. But if there's a multiverse, well, then basically it is only to be expected that at least one sub-universe has suitable constants for life, and maybe many of them have, even though they are just overall a slight, very, very tiny minority. But then, because of an observation selection effect, we couldn't have found ourselves anywhere where the conditions are not friendly to life. So it's unsurprising that we find ourselves in one of the few universes that are life friendly. So the argument by suggested inference to the best explanations, then there is probably a multiverse, because this is a parsimonious explanation of why we exist, even though this seems to require such fine-tuning. You can often this argument is given in Bayesian terms. Here's a very simple, or I might say simplistic version of it. So you have a single universe hypothesis U, a multiverse hypothesis M, and then the evidence that there is a universe with the right constants for life. There's a life-friendly universe, and then you can make a likelihood comparison. It seems that just if there's just a single universe, you because of the required fine-tuning, you wouldn't expect the universe to be life-friendly. But on the other hand, if there is a multiverse, it's quite unsurprising that at least one sub-universe is life-friendly. So this likelihood seems far greater. So now, if you do this in fully Bayesian analysis, you also need priors for U and M, and if they don't dramatically prefer the single universe hypothesis, then for the posteriors, the rational degrees of belief in those hypotheses after conditioning on the observation that there is a universe with the right constant seem to privilege the multiverse. So it's not clear actually whether this argument goes through. It remains very controversial, and I get papers to review on this basically every 2 months, and would probably get them more often if I always accepted them. The first problem is that R contains information about our own existence, right? Or we can the negation of R would entail that we don't exist, and it's not something that we can observe. So that makes it very unclear what could be rational priors for U and M. So those priors would be prior probabilities that we assign to U and M, not taking into account knowledge that we exist. Right? We would have to say, well, how probable is it that is it just a single universe or it's a multiverse? But we have to make these considerations based on which we assign those probabilities, while neglecting our knowledge about our own existence and everything that comes with it, right? Everything else that we know about the world is somehow tied to our existence. So it's very unclear how we could assign any priors based on this. This is a problem. It depends a bit on how good the justifications are that you generally want for priors, but here the prospects seem rather bad for those. Another potential problem is that this might invite the inverse gambler's fallacy charge. So the inverse gambler's fallacy, it's quite funny and interesting to know, is a fallacy that is committed by someone who thinks from one remarkable observation that there have been many other less remarkable events, even though this is not something that they can rationally conclude because the events are actually uncorrelated. So imagine someone who comes into a casino and finds a remarkable outcome. Maybe 5 dice were tossed and as all of them show a 6, and this is like something that it's the favorite combination of the person that comes in, and then they say, wow, you must have been playing for many hours for this to happen. But this is of course fallacious, unless they have waited until that visitor came to the casino until they showed him or her. But otherwise, whether there are other independent tosses doesn't make it any more likely that there is that there are 5 6s on this one toss. So it's a fallacy, and the proponents of this fallacy argue that the inference from fine-tuning for a multiverse commits the same fallacy. The idea would be that they find, oh, this universe is very remarkable, it has the right conditions for life, so so there must be many other universes with less remarkable conditions, and this then seems just as fallacious, right? There is an important difference that is also widely acknowledged, namely that in the casino case, the person who comes in could have witnessed another outcome, right? There's nothing that makes this impossible. It's just they happen to find that remarkable outcome. On the other hand, we couldn't have found conditions that are not life-friendly in our universe, so this is a huge disanalogy. But the proponents of this inverse gambler's fallacy charge say that the right casino analogy is actually then still different, and ultimately the fallacy is committed. It remains contentious. I think a generally better way, which I pursued in my book and in a paper called A New Fine-Tuning Argument for the Multiverse, uses our existence as background information, and then tries to assign probabilities for single universe and multiverse hypotheses based on that. On that evidence, taking as new information the insight that, at least according to the fine-tuning claims, Carr and Rees and so on, the laws are such that only for specific values of the constants life is possible. And I think the argument can be saved to some extent, but you need an independently plausible, concrete multiverse theory for it to be appealing. Yeah. So we are then, that motivates the question that this talk is ultimately about, namely the prospects to which we can, for testing concrete multiverse theories, for instance, to the extent that it's concrete, the landscape multiverse theory. Some, such as Peter Voigt, but also many others, say that this is impossible. Other universes are not detectable, so we can't make, basically by definition, or because we are not able to causally interact with them, like bracketing things such as so bubble collisions. Because science is empirical, right? So this is just not possible. However, so it's clear that to some extent this is not true. There is certainly a triple exception. So, like, if you have a multiverse theory that has no sub-universe in the multiverse, there's anything like the standard model, has anything like standard model physics, so that's ruled out, right? So, I mean, that sounds trivial, but it is still interesting to note. Another maybe more interesting exception is if you have a multiverse theory that in some respects behaves not really like a multiverse theory, but more like a single universe theory, then maybe you can also test it to some extent. So I use the expression here that the constant scan, so that means that they are different in different sub-universes. So we could have a multiverse theory that for some parameters, like aspects of the laws or constants in our universe, fixes them and actually predicts the observed values very nicely. But others, for others, it doesn't fix them, and actually for them, it also would make sense to say that they are randomly distributed. So it could be, for instance, that we find a theory that predicts the value of the cosmological constants, but doesn't predict the value of the quark masses, and rather predicts, it makes it natural to expect a distribution of quark masses that is, of which the one that we find is actually quite representative. So this would be, to some extent, provide evidence for such a multiverse theory, right? In general, the hope that is pursued in the literature where this is then concretely tried is to use what is sometimes called an anthropic approach. So to say, by definition of multiverse theory, at least some constants scan, but which values would typical multiverse inhabitants find? So we cannot just say which values would be typical, would obtain in most universes, because those might be lifeless, observerless. We would have to focus on those values that are found typically by observers. And there is the example that I found in the literature that maybe tries to do this most explicitly is inspired by the old Weinberg observation from the 1980s, according to which the value of the cosmological constant lambda is constrained to about 1,000 times what we now find it to be. It wasn't known at the time. Otherwise, no galaxies would have formed. So that seems still this upper value of upper bound for lambda is still pretty large, but the Busso et al. In a paper from 2007 in Physical Review D argues that actually in the landscape multiverse, the majority of observers would find something in an interval here between 4.2 times 10 to the minus 124 and 5.8 times 10 to the minus 122. The measured value lies just in that interval, so it seems just basically is perfectly predicted by the landscape multiverse theory according to their calculation. So this would seem to be a predictive type for string theory and internal inflation. So remember that, like, for theoretical reasons, we would expect a much larger value. So this anthropic prediction seems to get it right. So this would seem to be very strong evidence for the landscape multiverse. There are arguably, and now I come to why I think the prospects for these kinds of attempts are still pretty bleak. There are at least two very big problems with this. So first is, and they are basically acknowledged by Bussard et al., but the ways of dealing with them are arguably quite unsatisfying. So the first problem is the measure problem of cosmology. Because the inflationary universe is infinite, some regularization is needed, some way of counting. Here the common strategy is to just consider various measures that somehow make sense systematically, like proper time measures, or they use a causal diamond measure or causal patch measure in this case. The common strategy is to just rule out measures empirically, to see which ones work and which give absurd results, which they don't often do. But arguably, there is no fact about what the correct measure is. So if you there's no, it's not that God somehow fixes a measure and we have to discover it. We can just see which measure delivers predictions that then accord with what we actually find. And another problem is how we should count observers. Right? This is maybe an even more obvious problem, and more general, even if we had this problem with the infinities were absent. So of course, observer is not a physical notion. It's not a notion from fundamental physics, and there might be so for instance, when we have now more advanced AI systems, do they count as observers? Like do lay people who are not physicists or non-cosmologists, do they count as observers? Right, whatever. It's very difficult to decide what should count as an observer. Here the idea is that it doesn't really matter, and we can just use some proxy that basically does the job of mimicking observer number for reasonable definitions of observers. Examples that are used in the literature are, for instance, a galaxy matter per baryon, like how efficiently baryons are converted into galaxies, or entropy production in the causal diamond. But the problem here is that this is not a controlled approach. Observers are high-level phenomena, and they are not physically fundamental. So you can basically create a lot of outcomes, and ultimately, if you constrain both of these choices, cosmic measure and observer proxy, according to what works, it's not very remarkable in the end that you get a prediction that actually works, that accords with what is empirically found. To see how this is really something that is not unique to cosmology. I will in a minute bring into play the notion of observer degrees of researcher degrees of freedom from the social sciences. So I quote here first to make it a bit more clear how this happened. This is a quote from the Bussard et al. Paper. They write, the causal entropic principle, and entropic is here a wordplay on anthropic. The causal entropic principle asserts that physical parameters are most likely to be found in the range of values by which the total entropy production within a causally connected region is maximized. Despite the absence of more explicit anthropic criteria, the resulting probability distribution turns out to be in excellent agreement with observation. In particular, we find that dust heated by stars dominates the entropy production, demonstrating the remarkable power of this thermodynamic selection criterion. So in practice, they focused on a simplified version of our universe. They treat it as containing only pressureless matter and a cosmological constant. So there's another modeling freedom here. So if this hadn't worked, they could have refined the model to include more realistic aspects of our universe. Then they restricted attention to a causal diamond and assume that the observer density is proportional to the entropy gradient, and this enabled them to give this sort of prediction for the value of lambda. So now the announced comparison with social sciences, here this is a quote here that I give you from a seminal paper by Simmons, Nelson, and Simonson. While the context for which this quote is the replicability of the replicability crisis of the social sciences. You may have heard about this. So in the 2000s, it became clear that a lot of the published research in the social sciences was actually quite unreliable. So many effects, for instance, like how beneficial power posing is to your results, or I think the stereotype threat results. So they were tested again with more high-powered studies often, and then the effects weren't observed, couldn't be reproduced, and this threw into doubt a lot of social science. So how could this happen? Well, of course, partly it has to do with career incentives and maybe outright fraud, but often not outright fraud. Actually, many practices widely thought to be benign were exposed to actually be very problematic. I think just the kind of approach that Bussa et al. Pursued is also similarly problematic, even though it's believed to be benign. So without further ado, I give you this characterization by Simmons, Nelson, and Simonson. The couplet is a construct we refer to as researcher degrees of freedom. In the course of collecting and analyzing data, researchers have many decisions to make. Should more data be collected? Should some observations be excluded? Which conditions should be combined and which ones compared? It is common and accepted practice for researchers to explore various analytic alternatives, to search for a combination that yields statistical significance, and to then report only what worked. For instance, a relatively egregious example of this is p-hacking, that you look into your data and you generally don't find the effect that you might have been looking for, but you find it, I don't know, if you restrict to Catholic girls or so, or immigrants who have come after 1990 or so for a specific group, and then you report that and don't report what hasn't worked. But actually, given all the variables that you have considered, it's only to be expected that for some combination of variables you do find the effect. Right? So here the parallel would be that it's only to be expected that for some combination of cosmic measures and observer proxies and maybe other modeling assumptions, you would find the value that you're looking for, especially if you use that as the explicit criterion for whether, say, a measure, an observer proxy, or modeling assumptions are acceptable. Right? So according to my impression, the observer proxy and the cosmological measure are effectively researcher degrees of freedom, and actually of the nastiest type. So what does not work is treated as it were ruled out empirically. So no wonder that you can get to outstanding predictions, right? And add a bit of publication bias or so, and the pressure to publish something that looks encouraging, and the result is not very remarkable then. So that doesn't mean that we can never get good evidence for a multiverse theories. In particular, here the possible hope would be that we find something like a partial multiverse or only some parameters scanned. So for those, there doesn't make much sense then, if that's the case, right, to ask why are their values what we find them to be. But for other constants, we can maybe get fantastic prediction of how they are related is really fantastically predicted by the theory. That could be. And that possibility is not ruled out. But on the other hand, as long as this is not a multiverse theory, it doesn't behave like a single universe theory in many respects, then given researchers' confirmation bias and all these things, all claimed predictions from multiverse theories are, in my view, to be regarded with a significant amount of suspicion. So to conclude, let's hope, just for the progress of future physics, that we do not live in a multiverse, or at least to the extent that we do, that it behaves like a single universe in many important respects. Many thanks for your attention.